We'll first hone in on the time leading up to convective initiation. This is a time in which you'll mostly be looking at those other tools in your toolkit, along with using your eyes, but radar does come in handy before storms fire, particularly in the identification of boundaries. Boundaries denote the interface between cooler, more stable air and warmer, more unstable air, and often show up on radar reflectivity as fine lines, even though the boundaries themselves don't produce precipitation. This is a product of the fact that winds generally come together or converge along boundaries. As winds converge along a boundary, so do particulates, dust, water droplets, bugs, etc. These conglomerate, and the radar beam detects this increased concentration of particles, forming a fine line that demarcates the boundary's location. As you may know, surface boundaries often become a focus for convective initiation, and tornado chances can increase in supercells that track along boundaries, so identifying them is a critical part of the forecasting and nowcasting process. Surface observations and satellite imagery may often be more reliable tools to use to locate boundaries, but radar can still be helpful as well, especially in diagnosing the motion and intricate structure of the boundaries themselves. When you're forecasting or selecting a target for a particular chase day, it's good practice to take a look at the radar going back to the evening prior to the event in question. This can help you identify any potential boundary-producing convective complexes that may have traversed the area of interest in the lead-up to your chase. These complexes can emit ample rain-cooled air or outflow, which often leaves behind an outflow boundary or boundaries in its wake. To do this, a radar mosaic, such as the one from the College of DuPage website, can be helpful, as it gives a broad-scale view of the data from all the radars in an area, not just one radar, in a single image or loop.
Join our channel membership and unlock instant access to full-length storm chasing presentations. Click the subscribe button below and then select join, or just click the join button on our profile page.
In this example from May 24, 2008, an expansive convective complex developed on the evening of the 23rd and persisted through the morning of the 24th. Behind it, we would expect to see a mass of rain-cooled air, whose southern extent would be demarcated by an outflow boundary trailing from the complex's southern flank. The outflow boundary itself was somewhat unclear on mosaic radar, but surface observations confirmed its existence, and sure enough, a tornadic supercell developed along it that afternoon. While many outflow boundaries do favor increased tornado potential in storms that track along them, this is not always the case. The boundary must be oriented relatively parallel to storm motion so that storms can anchor to and track along it. Otherwise, storms may quickly cross the boundary into cooler, more stable air, which is unfavorable for tornadoes. The movement of the outflow boundary must be assessed as well. Slow-moving or stationary boundaries are most favorable for tornadic supercells, as they give storms a better chance to track along them without getting undercut by cool, stable air. Boundaries that move quickly or surge are still able to initiate storms, but they quickly move to the cool side of the boundary, becoming elevated above the cooler, more stable air, and losing access to warm, moist inflow that exists on the warm side of the boundary. Elevated storms have very low tornado potential because of this, while storms that track along or on the warm side of a boundary are typically surface-based, meaning that they're able to draw in inflow rooted at the surface that's warm, moist, and unstable, which aids in tornado production. Sometimes these rules can be ignored if the boundary is diffuse, in other words, when the change in temperature is more subtle across the boundary. In these situations, the air on the cool side of the boundary may not be stable enough to inhibit surface-based storm development, and generally more backed surface winds on the cool side of the boundary, i.e. more southeasterly or easterly winds, can increase low-level shear to aid in supercell tornadogenesis, even though the storms are technically displaced to the cool side of the boundary. This happens somewhat frequently in higher terrain areas like Colorado or the Caprock of West Texas. A look at surface observations can provide confirmation of how strong the temperature gradient is across a boundary. Another type of boundary that's similar to an outflow boundary is a sea or lake breeze boundary. These exist in coastal regions like Florida and in areas near the shores of large lakes, such as in the Great Lakes region. On sunny days, the ground heats up more quickly than the water, which induces a circulation that draws cooler air inland from over the water source. The interface between the warmer inland air mass and the cooler air mass moving ashore creates a boundary, and it can often help initiate thunderstorms in the same way that outflow boundaries do. Terrain-induced convergence boundaries can also show up well on radar. These develop when topographical features manipulate airflow around them such that low-level winds converge and they can provide the impetus for storm development. These boundaries are typically stationary, but because they are simply wind shift boundaries and do not involve temperature gradients, it doesn't matter which side of the boundary storms develop on or migrate into in terms of whether they are elevated or surface-based. As we mentioned previously, along the boundary itself and the side of the boundary that has more backed low-level winds tends to be most favorable for tornadic supercells as long as the other ingredients are in place. In this example, the fine line on reflectivity you see here denotes northern Arizona's Mogollon Rim Convergence Zone, or MRCZ. Within the Little Colorado River Valley, winds typically flow from southeast to northwest overnight through the morning and early afternoon. When the background flow takes on a westerly component, winds converge within the river valley, and the development of the MRCZ occurs. The Denver Convergence Vorticity Zone, or DCVZ, in northeast Colorado is another notable one. The DCVZ occurs when low-level southeasterly winds flow up and over the Palmer Divide, an east-west protrusion of higher terrain just south of Denver. Due to friction, these winds bend toward the northwest and can collide with northwesterly winds flowing down the slopes of the Rockies, creating a convergence zone that's typically situated just east or southeast of Denver. In this example, note the stationary fine line in reflectivity that was draped through the eastern portions of the metro, evidence of a DCVZ boundary in place. When analyzing these terrain-induced convergence zones, you can also use the velocity product to identify areas of vorticity or spin along the boundary, which can be stretched into the vertical to aid in non-supercell landspout tornadogenesis underneath nascent updrafts. Fronts and drylines can also be identified using radar, and the reflectivity fine lines associated with these features can often be quite sharp, like this dryline in southwest Kansas. As you may know, the dryline is a boundary between hot, dry air to the west and warm, moist air to the east that can initiate storms in many severe weather environments. Prior knowledge of the environment is necessary to correctly identify which type of boundary the radar is depicting. In addition to identifying boundaries, radar can also help you see areas of circulation. These circulations can be convection-induced or terrain-induced. One of the best examples of the latter is the Denver cyclone. The Denver cyclone is not the same thing as the DCVZ, which we mentioned earlier, but both have to do with the terrain features present in northeast Colorado. The Denver cyclone is a cyclonic or counterclockwise circulation that develops within the lower elevations in and around the Denver metro area as low-level southeasterly flow goes up and over the Palmer Divide. The flow is both bent by friction toward the northwest as it goes over the Palmer Divide and blocked by the massive obstruction that is the Rocky Mountains, so it curves back to the south and creates a cyclonic circulation. A DCVZ boundary often does develop when the Denver cyclone is in place, but it can occur without the assistance from the cyclone as well. Here's an example of the Denver cyclone in action. Notice the broad counterclockwise flow in the weak reflectivity echoes near Denver. These kinds of circulations can produce enhanced lift that promotes thunderstorm development and provide additional low-level vorticity or spin along with the enhanced low-level wind shear, especially where winds are most backed, that can favor tornadic activity of both the non-supercell and supercell variety. Radar can also highlight circulations in the form of horizontal convective rolls. Called HCRs for short, horizontal convective rolls are adjacent vortices that rotate opposite one another, exist in groups, and are oriented horizontally, generally parallel to the average wind in the low levels of the atmosphere. Within the region where HCRs are present, long streets of cumulus clouds develop within the rising branch of the circulations, i.e., where wind converges between adjacent convective rolls. HCRs are commonly found in the warm sector prior to and sometimes during convective development and are often a sign of lingering low-level stability. Once this stability erodes, so will the HCRs, and storms can initiate and become surface-based. If storms move into an area where HCRs remain stubborn, they may remain somewhat elevated. In this example, widespread horizontal convective rolls were in place across southwest Oklahoma and northwest Texas leading up to and during convective initiation, but notice how they erode with northern extent as storms mature. The storms move into the HCR-free area of southwest Oklahoma and become quite robust, going on to produce a significant tornado later on in the day. Sometimes HCRs can actually initiate storms themselves, especially when they intersect a boundary such as a dryline or outflow boundary. Alright, now that we've talked about how to use radar during the pre-convective stage, let's move on to convective initiation. Knowing where storms are initiating is critical in how you adjust your target and navigational strategies on a chase day. Again, other tools can help with this, such as satellite and visual reconnaissance, but often radar can provide the first clue that storms are initiating. The easiest thing to look for is what we call blips on reflectivity. These are small spots of slightly enhanced reflectivity that appear seemingly out of nowhere and are the first sign that nascent updrafts are producing precipitation. Blips will often go on to become robust storms, but in certain situations they may fail to intensify and even fizzle out before new blips take off. This means that either the cap is still a bit too strong to support updraft maturation, choking off the young storms before they can intensify, or the background forcing is still too weak. In other words, the atmosphere has destabilized enough to support storm initiation, but large-scale forcing for ascent is too weak to support the maintenance of those storms. A working knowledge of how the environment is evolving is key to understanding why storm maturation attempts are failing. One radar product that's useful in monitoring updraft intensity during and after initiation is the EchoTops product, which shows the maximum height of precipitation echoes detected by the radar that exceed 18 dBz between 5,000 and 70,000 feet above radar level.
Join the Storm Chaser Coaching Discord server and get instant access to a rapidly growing storm chasing community. Once you've joined, you'll be able to chat with our coaches, get your questions answered during weekly live office hours, and discuss strategy in the forecasting and storm chasing forum. You can join the Storm Chaser Coaching Discord server right now via the link in the description.
A sister product to EchoTops is Enhanced EchoTops, which helps smooth out irregularities that can sometimes appear in EchoTops output and identifies areas where the radar could not compute a cloud top height. However, the crux of what each product represents is the same. In essence, they estimate the height corresponding to the top of an area of precipitation, and they can be a decent proxy for how tall developing or ongoing thunderstorms are. For example, the value at the center of the bullseye in this enhanced EchoTops image is 62,000 feet, which means that the radar found the highest level at which there were precipitation echoes greater than 18 dBz to be 62,000 feet above radar level. The greater the EchoTops value is at a given point, the taller and stronger the updraft or storm is. Prior to the point at which precipitation reaches the surface, EchoTops can help you identify which updrafts are strongest and may turn into bona fide storms. In a typical severe weather setup, you may see EchoTops readings of 30 to 40,000 plus feet before precipitation occurs at the surface with a given storm, so this can be a good sign that storms are initiating. Of course, storm height depends on the vertical configuration of the instability profile, so this is not always the case, but in a good chunk of severe weather setups, this works fairly well. After initiation, the EchoTops product can tell you which storms in a batch of young storms are the most robust and may hold the greatest severe weather potential in the near term. Now, just one note about the EchoTops products. Never use EchoTops to analyze updrafts that are close to the radar site you're using. In these scenarios, the highest elevation angle that the radar is scanning may not come close to the actual top of the region of precipitation, which yields vastly underestimated or missing EchoTops data. Instead, select a radar that can still effectively sample the storms but is farther away. For example, even though these storms are near the Oklahoma City radar site, you'd want to use a site like Tulsa or Frederick to properly analyze EchoTops. Once storms initiate, radar can illuminate several signs of storm intensification. In a general sense, strengthening reflectivity and the development of tight reflectivity gradients signify that a storm is intensifying. Essentially, the storm transforms from somewhat of an amorphous blob to a much more shapely state, with a tight reflectivity gradient as you go in toward the center of the storm. In addition, the upward advance of strong reflectivities to higher and higher elevation angles also suggests that a storm is strengthening. Another sign of an intensifying updraft is the development of a bounded weak echo region, or BWARE, which is a small region of lower reflectivities surrounded by higher reflectivities in the mid-levels of a storm. A BWARE occurs when an updraft is so intense that it displaces developing precipitation particles to much higher levels within a storm, leaving a relative void in reflectivities. It's a sign that an updraft is quite strong and often indicates that a storm is becoming or has become severe. We can also continue to monitor the EchoTops or Enhanced EchoTops product to identify which developing storm or storms may have the highest severe weather potential. This can be a bit tricky as updrafts often fluctuate in intensity during the maturation process, leading to oscillating EchoTops readings. However, storms that are fairly consistently exhibiting the highest EchoTops may have the highest potential for severe hazards. Finally, something to watch for closely is splitting storms. This is simply when an individual storm splits into two distinct storms. The original storm, which is your right mover or right split, as it tends to move to the right of the mean flow, and a left mover or left split, which moves to the left of the mean flow. In supercell environments, left movers take on anticyclonic or clockwise rotation and tend to produce mostly large hail, while right movers rotate cyclonically or counterclockwise and can produce all severe hazards, including tornadoes. Storm splits often occur in the early portion of the convective life cycle thanks to the physics and dynamics intrinsic to supercells. Oftentimes, left splits will die off while right splits intensify. However, in certain environments, left splits are favored and can become robust, even more so than right splits. A telltale sign of a splitting storm is when a storm takes on the appearance of having two distinct reflectivity cores. In this example, note how reflectivity is enhanced on the northern flank of the ongoing storm alongside the enhanced reflectivity within the ongoing storm itself. We then see a clean break, with the left split moving off to the northeast and the right split intensifying and moving off to the southeast. This can also be confirmed visually via two separate precipitation shafts. Keep an eye out for splitting storms, as left splits can sometimes produce even larger hail than right splits, and left splits from separate areas of convection can interact or merge with mature storms, which can induce drastic changes in the mature storm's behavior, from complete dissipation to tornadogenesis.
Remember to check out those links in the description below, and then watch another video.